Deep within the vast emptiness of space, hurtling at astonishing velocities amid the shadow-separating stars, an astonishing entity is drawing near our solar system. Measuring 7 miles across and formed from ancient ice predating Earth, 3I Atlas traces a route so extraordinarily unlikely that it challenges any ordinary origin. Its journey will carry it beyond Mars, around the Sun's far side, close to our planet, and into Jupiter's magnetic field, following a pattern that resembles a deliberate scouting operation. We've long figured that any arrivals from distant stellar realms would just be inert stones and frozen remnants cast out from far-off planets. Yet suppose that's not the case. Suppose certain cosmic travelers aren't random drifters, but intentional messengers. Quiet observers dispatched by societies that mastered concealment in the interstellar gloom ages ago. On this episode of The Sleepy Explorer, we're delving into clues, suggesting that our enigmatic guest could mark humankind's initial encounter with alien minds. We'll unpack the Black Forest theory, unravel baffling probabilities, and probe the reasons 3I Atlas acts so differently from every celestial body we've observed before. The cosmos might hold far more life than we've imagined. Get ready. We start with the Black Forest theory, which posits that evolved societies stay intentionally concealed, deploying advanced probes masquerading as typical astral junk to monitor emerging planets such as ours. In contrast to the puzzling Oumuamua, or the standard comet Borisov 2I, 3I Atlas displays a meticulously planned route across our system, optimized for thorough surveillance yet flawlessly blending in. As this puzzling intruder embarks on its sweeping pass by our worlds, we're confronted with a scenario that might transform how we view existence among the stars. Is this our debut interaction with otherworldly smarts, or merely the greatest astronomical fluke in recorded history? To resolve this, let's plunge further into how 3I Atlas came to light. The tale of 3I Atlas unfolds not through a sudden epiphany, but via the steady diligence that characterizes contemporary stargazing. On July 1, 2025, at the Atlas Observatory in Rio Hurtado, Chile, computer-driven instruments picked up a dim speck shifting amid the fixed stars. The provisional label was A11PI3s, a placeholder offering no clue to the profound implications this find would soon carry. Atlas, the Asteroid Terrestrial Impact Last Alert System, stands as one of our species' premier detection grids for risky near-Earth threats. Backed by NASA and run from the University of Hawaii, it features 4 scopes placed strategically worldwide, each sweeping enormous sky sections on every cloudless evening. Built mainly to identify impact-risk asteroids, its broad-view tech also excels at catching oddities like extrasolar intruders. The Chilean scope, a 0.5-meter mirror fitted with cutting-edge CCD sensors, first marked A11PI3Z as just one more transient dot calling for additional checks. In today's automated celestial sweeps, scopes log thousands of such movers nightly. The majority proved to be routine main belt rocks, Earth-approaching bodies, or familiar comets swinging back inward. Nothing stood out right away about this one. It showed up dim at about magnitude 19, too faint for unaided eyes or basic backyard gear. Its drift relative to the stars seemed leisurely, hinting it remained well out from the sun. Such traits wouldn't typically trigger alerts in the software routines. The routine for verification. Navigating an interstellar path demands intricate calculations and thorough monitoring. The primary metric is orbital eccentricity, which quantifies the degree of elongation in an orbit's shape. Bodies tied to our solar system exhibit values below 1, resulting in bounded elliptical paths encircling the sun. Those exceeding 1 pursue hyperbolic paths, arriving from beyond our system and exiting without looping back. Early sightings of 3I Atlas indicated an eccentricity surpassing 1. However, validating such data calls for repeated evenings of accurate positional measurements. Factors like air disturbances, equipment inaccuracies, and the target's dim appearance introduce considerable variability in readings. Numerous candidates once thought to hail from interstellar realms have ultimately revealed themselves as peculiar solar system residents, such as comets or asteroids tracing extremely stretched orbits. Shortly following the first spotting, facilities worldwide initiated pursuit of the intruder. The European Space Agency's optical facility on Tenerife verified the elevated eccentricity figures. Arizona's Catalina Sky Survey contributed further location details. Come July 6th, a sufficient volume of data had gathered to dispel all uncertainty. This marked the third verified interstellar visitor to our solar system. The official naming procedure kicked off without delay. The International Astronomical Union's Minor Planet Center, serving as the worldwide hub for minor body finds, bestowed the designation C2025N1 Atlas, where the C denotes a comet-resembling body and N1 signifies the inaugural discovery in July's latter portion of 2025. The casual moniker 3I Atlas emerged soon thereafter, with the 3I denoting the third interstellar find. Astronomers worldwide responded swiftly and fervently. In contrast to the unforeseen arrival of Oumuamua that blindsided experts, the field had anticipated more such interlopers. Protocols for study were preset, models theorized, and resources primed for swift investigative efforts. Dr. Robert Warwick, who unearthed Oumuamua 8 years prior, remarked that spotting 3I Atlas evoked a sense of déjà vu, yet felt refreshingly novel. The verification routine mirrored past experiences, though this entity offered greater potential for in-depth analysis. Differing from Oumuamua, which was already receding upon detection, 3I Atlas remained inbound toward the Sun, granting extended windows for scrutiny over coming months. The hurdles in tracking 3I Atlas proved substantial yet surmountable. Upon initial identification, it lingered roughly 5.2 astronomical units from the Sun, comparable to Jupiter's orbit. Consequently, it endured scant solar warmth, rendering any potential cometary outbursts faint and elusive. Anticipated surges in visibility were projected as it neared perihelion on October 29th, its solar closest approach at 1:36 AU. Leading observatories promptly organized joint viewing initiatives. The Hubble Space Telescope reserved executive override slots for prompt imaging. The James Webb Space Telescope geared up for infrared spectral examinations. Terrestrial sites globally reprioritized timetables to monitor this uncommon guest. Hobbyists contributed vitally during the preliminary phase as well. Philip Romain, accessing iTelescope. Net's Zero, 51-meter mirror in Chile from afar, secured among the earliest validating shots, merely a day post-alert. His image, depicting a hazy blur amid stellar backdrop, captured one of humankind's initial views of this enigma from a distant stellar realm. As observations advanced into August, the early thrill started yielding to more organized investigations. Early assessments indicated that 3I Atlas wasn't merely another cosmic traveler from beyond our system. It represented a phenomenon possibly without precedent in terms of dimensions and actions. Conditions were ripe for launching one of the most thorough observational efforts in astronomical records. The finding of 3I Atlas served as a reminder to researchers that our solar system functions less like a secluded outpost and more like a pit stop on age-old pathways linking distant stars. Every such extraterrestrial guest grants a distinct glimpse into the forces molding worlds across the Milky Way. Moreover, 3I Atlas held the potential to deliver the sharpest insights so far into these universal dynamics. Crucially, 3I Atlas's vastness allows it to hold on to fleeting substances, such as frozen water, over immense timescales. Compact forms suffer from elevated surface-to-bulk ratios, shedding such elements swiftly via evaporation and cosmic wear. In contrast, a behemoth like 3I Atlas could shield its core in near-perfect state for billions of years, acting like a preserved relic that captures the environment of its birth star's domain. Pinpointing 3I Atlas's exact form demanded meticulous light variation studies, tracking shifts in its glow during spins. Such data uncovered a spin cycle of about 4 hours, meaning it completes a turn every half of an Earth day or so. The subtle fluctuations in luminosity over this cycle imply that 3I Atlas approximates a ball shape, unlike the stretched-out profile of Oumuamua. This almost round configuration stands out as especially noteworthy, offering key hints regarding its beginnings and past. Stretched forms like Oumuamua hint at shaping by intense gravitational strains or even engineered design. Roundish ones, though, generally arise via gradual buildup mechanisms, enabling gravity to shape objects into nearly spherical forms, played a key role here, much like those responsible for crafting the planets and satellites in our solar system. The albedo, or light-reflecting property, of 33rd Atlas turned out to be quite dim, hovering near zero, ERO 4, which means it bounces back just roughly 4% of incoming sunlight. Such dimness is common among comet cores, often likened to soot darker than coal because of their abundance in organic materials and carbon-laden rocks. This subdued reflectivity stood in stark opposition to the exceptionally bright surface of Faux Oumuamua, hinting further that 3I Atlas could serve as a standard specimen of matter from beyond our stars. Mass calculations for far-off bodies are infamously tricky, relying on either the gravitational tugs they exert on nearby items, which 3 Atlas was too remote and solitary to offer, or guesses about density drawn from makeup details. Drawing on spectral readings that pointed to a blend of ice and stone akin to comets from the distant edges of our own system, scientists pegged the mass of 3 Atlas at about 1.2 trillion kilograms, comparable to a modest earthly peak. This vast bulk, paired with the item's largely untouched condition, implied that 3 Atlas might hold onto substances from the birth era of its home star cluster. In contrast to tinier visitors from interstellar voids that could show signs of weathering or change, 30 Sun. Atlas likely harbors untouched frosts and crystals that solidified straight from the swirling gas and dust around a faraway young sun. Density figures, pulled from mass and size measurements, came in at roughly a vero, 66 grams per cubic centimeter, far lighter than dense stone, yet fitting for a combo of frozen water, carbon-based stuff, and gritty particles. This makeup aligned closely with predictions for hefty comet hearts born in the chilly fringes of star systems, where conditions stay cool enough for water and other fleeting gases to solidify. As data poured in during July and August of 2025, a clear image took shape of 3I Atlas as an untouched leftover from the building phase of some alien solar setup. Its impressive dimensions, sparse weight per volume, and rounded contours all pointed to slow buildup in the frozen outskirts of a remote world-building zone, then a slingshot into the void via pulls from giant worlds. Still, these apparently simple traits marked only the start of the enigmas tied to 3I Atlas. Deeper probes into its makeup and path soon uncovered puzzles that defied easy answers and hinted at wilder scenarios. The immense proportions of 3 Atlas, towering over every prior interstellar find, marked a huge advance in probing stuff from alien suns. At last, stargazers could scrutinize a space wanderer big enough for in-depth chemical breakdowns, advanced path simulations, and maybe even close-up probe visits. The groundwork was laid for findings that could overhaul our views on how worlds take shape and the odds of smart life across the cosmos. The makeup of 3I Atlas stands as a landmark in studies of such drifters, offering fresh peeks into the building blocks and birth mechanics of a far-off star family. As it drew nearer to our sun over the 2025 summer months, beefier scopes zeroed in to unpack the faint glow's hidden chemical clues. The initial big reveal stemmed from scans via the NASA Infrared Telescope facility atop Mauna Kea in Hawaii. With its sharp spectrometer, experts spotted bold dips in the light spectrum matching frozen water. This finding, spanning various infrared spectra, came as no great shock. Icy water abounds in comets across our solar system. Yet the properties of this particular ice unveiled an extraordinary narrative. In-depth examination of its isotopes indicated that the frozen water in 3I Atlas stands apart from any H2O detected elsewhere in our cosmic neighborhood. The deuterium to hydrogen proportion, a vital marker for tracking water's beginnings, displayed ratios unseen in Earth seas, Kuiper belt comets, or the earliest meteorites. This unique isotopic profile offered irrefutable proof that the water within 3I Atlas solidified in a wholly distinct stellar setting, perhaps around 7 billion years back. The untouched quality of this primordial ice holds immense value for science. One simply can't overemphasize it. Nearly all water in our system has endured repeated phases of warming and chilling across 6 billion years. Comets venturing near the Sun shed outer layers via sublimation, whereas water on asteroids and planets undergoes modifications from heat and chemistry. In contrast, the water inside 3I Atlas seems to have stayed iced and pristine from its initial creation, safeguarding a vivid snapshot of its originating system's environment. Further spectral scans via the Gemini South Observatory in Chile uncovered organic substances woven into the body's makeup. Elaborate carbon-based chains, such as methane, ethane, and even more intricate organics, appeared right next to the ice. These compounds hinted that 3I Atlas originated in a zone brimming with carbon and heavier elements, likely orbiting a star whose metal content diverged from our own sun's. Carbon-laden minerals further complicated the makeup profile. Spectral signatures matching organic polymers and kerogen-like substances pointed to substantial quantities of refined organic material in 3I Atlas. On our planet, these often link to life processes, though in the cosmos, they arise from straightforward chemical interactions with basic organics and cosmic rays. Most captivatingly, the organics in 3I Atlas exhibited isotopic balances, implying birth in an oxygen-heavy milieu. This points to roots in a star system where oxygen outnumbered carbon more than in our local stellar patch. Such scenarios might develop near-age stars that have cycled through several rounds of nucleosynthesis, loading their protoplanetary disks with dense elements. When stacked against standard solar system comets, the contrasts went well past basic isotopic variances. Those born close to our Sun bear signs of heat treatment, including ones that lingered in the chilly fringes of the Kuiper Belt or Oort cloud. They harbor crystals that demand intense heat to form, implying they gathered stuff once near the proto-Sun prior to outward migration. 3I Atlas, by comparison, lacked any trace of such heating. Its mineral setup aligned with freezing at ultra-low temps, maybe under 30 Kelvin. This points to assembly in the farthest fringes of a remote star's disk, distant from its central warmth. Without hot-formed minerals, it suggests 3I Atlas coalesced right there in the frigid outer disk of its home system, not blending in relocated inner materials. The research potential of this unspoiled blend reaches far past mere interest in far-off realms. 3I Atlas serves as a pure specimen of protoplanetary disk stuff from another sun, enabling scientists to probe theories on how worlds take shape under varied conditions. The object functions as an ideal natural lab for examining how factors like stellar metallicity, protoplanetary disks, and more shape the kinds of substances used in building planets under varied chemical and physical environments. Spotting intricate organic compounds carries deep significance for the field of astrobiology. Although such substances might arise from abiotic reactions, finding them in an untouched interstellar visitor shows that life's chemical building blocks can arise and endure across vast cosmic epochs. Such a discovery reinforces the idea that organic chemistry emerges inevitably from the mechanisms of star and planet creation across the entire Milky Way. During ongoing observations in August 2025, further insights into the object's makeup surfaced, offering key details for grasping its path and dynamics. Minute traces in the icy components pointed to origins near a star boasting about 1.3 times the metal content of our Sun. This could be a star roughly 2 billion years more ancient than ours. That greater antiquity could account for the odd isotopic patterns and the plentiful refined organics present. Ratios of nitrogen isotopes in 3I Atlas offered hints to its beginnings as well. The 14N-15N proportion indicated development in a star's vicinity with nucleosynthetic activities distinct from what forged materials in our solar system. Astronomers hope this isotopic marker will one day pinpoint the exact stellar setup that birthed 3I Atlas. Even more striking, the makeup study uncovered no signs of major space weathering or changes over the course of its interstellar voyage. Even after possible billions of years facing cosmic rays, galactic magnetic forces, and the interstellar medium, 3I Atlas seemed to retain its initial makeup with hardly any modifications. Such intactness implies either a brief trip through space or robust shielding of inner layers by the exterior shell. Holding on to these age-old substances in 3I Atlas marks a groundbreaking chance for science. Scientists now get to probe stuff formed by a foreign star, kept pristine for billions of years. Acting as a celestial vault from the past, it sheds light on how planets take shape, the chemistry of stars, and how life's ingredients spread galaxy-wide. Yet, as in-depth data on composition piled up, certain experts started spotting minor oddities that clashed with typical comet development frameworks. These inconsistencies would fuel rising theories on whether 3I Atlas could be something beyond just an ordinary frozen, rocky interstellar fragment. The route 3I Atlas takes through our solar system stands out as one of the least likely paths logged for any sky body. While experts fine-tuned their models over the 2025 summer, the exact math of its course started sparking doubts about standard views on how orbits work naturally. 3I Atlas enters our system via a sharp backward path, moving counter to the planet's spin around the Sun. Such a backward course isn't rare for interstellar guests, since arrivals from distant systems might come from any angle in 3D space. The standout feature of this path lies in its exact match with core planes in our solar system. Its orbital tilt stands at 162 compared to Earth's path, fitting what experts term an almost pole-to-pole backward orbit. Though it may seem haphazard, closer scrutiny shows how this tilt produces a striking correspondence. This path ensures the object's visibility from Earth is optimized throughout its journey across the inner solar system. Remarkably, 3I Atlas will stay visible to ground-based telescopes for the whole duration of its stay, without vanishing behind the Sun for long stretches like so many other bodies do. The route features a lineup of planetary flybys that appear meticulously planned to boost scientific study chances. On October 3, 2025, 30 Atlas will zip by Mars at a mere 18 million miles, near enough for in-depth scrutiny from various probes circling the reddish world. This timing hits during Mars's morning hours, ideal for spotting any emerging coma or tail as the comet nears its Sun closest approach. After swinging past Mars, Thur-2, Atlas will hit its perihelion on October 29, 2025, at 136 AU from the Sun. Positioned just beyond Earth's path, this spot keeps it safe from major gravitational tugs while allowing intense solar warmth that could spark a coma. The perihelion's placement on the Sun's opposite side from us poses a viewing hurdle, resolvable only via probes at the L1 Lagrange point or around Mars. Afterward, the outbound path keeps up these fortuitously timed planetary brushes. By December 19, 2025, Atlas will glide about 170 million miles from Earth nearby for sharp views via the James Webb Space Telescope and the Vera C. Rubin Observatory, yet distant enough to sidestep any tidal effects on the comet or our world. The standout flyby happens on March 16, 2026, as Thur-4 Atlas skims a scant 33 million miles over Jupiter's stormy clouds. At that range, it dips into the gas giant's magnetic field, positioning it for possible material grabs by the Juno mission. The setup indicates 3 Atlas will traverse parts of Jupiter's magnetotail, where energetic particles and comet dust could get snagged for examination. Crunching the numbers on this orbit yields odds so slim they question standard ideas of haphazard paths. The exact match to Earth's orbital plane carries under a 0.2 chance of random occurrence. Factoring in the pinpoint flyby ranges and schedules pushes the total odds to roughly 1 in 20 compelling enough to explore deliberate origins. This route also mirrors what you'd want for a scouting probe eyeing our system's big worlds. Sequenced peaks at Mars, prime Sun proximity for gear tuning and energy boosts, smart Earth alignment for signals or watches, and a tight Jupiter pass to probe the solar system's mightiest magnetic zone. Were 3 Atlas an engineered visitor probing our system, you'd be hard-pressed to devise a better itinerary. It grants entry to diverse planetary zones, sustains peak solar energy spots, and builds in stealth phases when it's eclipsed by the Sun or too far for Earth eyes. Moreover, the brisk inbound speed of 3I Atlas around 33 kilometers against the Sun points to routes beyond our nearby cosmic turf. Ejects from close stars usually slow down from the Milky Way's star crowd pull. The zip of 3I Atlas hints at a birthplace in some far-flung star cluster. The trajectory lacks any signs of artificial propulsion, exceeding the boosts from natural gravitational assists. The backward orientation of its path also allows for effective collection of solar system substances that would be tough to gather using a forward-moving route. As 3I Atlas travels counter to the typical movement of solar system debris, it runs into a denser stream of dust, ionized particles, and various fragments, offering insights into the composition and structure of our stellar neighborhood. Gravitational simulations of the route uncover yet another fascinating feature. The course seems deliberately fine-tuned to steer clear of near misses with the outer giants during the inbound leg. Saturn, Uranus, and Neptune sit in positions that limit their pull on 3I Atlas, avoiding major path shifts that could disrupt the meticulously planned series of close passes through the inner realms. Certain experts have observed that the route closely resembles those computed for imagined interstellar explorer projects from human space programs. Analyses by NASA, ISA, and similar groups have plotted ideal paths for voyages to neighboring stars. Many of these conceptual routes exhibit traits akin to 3I Atlas's real path across our solar system. The accuracy of this path stands out even more against the hurdles of navigation across the void between stars. Any traveler spanning stellar distances has to factor in star drifts, galactic spins, and pulls from diverse gravitational fields. Reaching the exactness shown by 3I Atlas demands either incredible chance or advanced course adjustment and steering tech. Skeptics of the artificial source theory argue that selective perception could be shaping views of what might just be an astonishing fluke. With trillions of bodies across the galaxy and endless trajectory options, even the rarest occurrences happen now and then. Humanity's habit of spotting meaning and intent in chaos could be fabricating importance out of nothing. Still, the numerical exactitude of the path's precision is hard to overlook. Be it from random cosmic chance or deliberate engineering, the route of 3I Atlas via our solar system marks one of the most flawlessly executed showcases of heavenly dynamics on record. As the entity presses onto its closest solar approach, hands-on scrutiny of how it reacts to sunlight warmth and tidal forces might at last uncover its essence. The voyage of 3I Atlas across our solar system follows an exacting dance of the heavens, yielding rare chances for research. Every key point along this route opens a distinct view into the entity's core, with alignments and schedules that feel tailor-made to deepen our grasp of this enigmatic guest. The 3rd of October 2025, Mars Flyby. The initial big event happens as 3I Atlas sweeps by within 18 million miles of Mars, drawing nearer to the rusty world than any prior interstellar wanderer. This brush occurs amid the Martian sunrise phase, yielding prime illumination for space and ground watchers alike. Several probes active around Mars will gain exceptional views of the object in this pass. NASA's MAVEN Mars Atmosphere and Volatile Evolution mission, built to probe the planet's upper air layers, can pick up any outgassing from 3I Atlas via its array of analyzers. The European Space Agency's Mars Express orbiter will add sharp photo tools, while China's the Tianwen-1 orbiter offers extra viewpoints for monitoring the object. Ground observers on Mars, such as NASA's Perseverance and Curiosity rovers, could capture images of it provided the atmosphere cooperates. Since the flyby happens at dawn, the item will stand out against the night sky, enhancing visibility for photos. This close pass by Mars holds special importance as it takes place while 3I Atlas is heading toward the Sun, prior to any major cometary behavior kicking in. Detecting any coma or tail formation at this stage would indicate either an atypical makeup or deliberate venting processes, since regular comets usually show no visible coma until they get within 2 to 3 astronomical units of the Sun. The projected angular dimensions of 3I Atlas during the Mars pass will enable exceptional resolution in imaging efforts. Assuming it holds its estimated 7-meter width, it ought to show up as a distinct disk in sharp images, possibly exposing surface details, spin properties, and uneven venting effects. On October 29, 2025, perihelion arrives. The peak intensity in 3I Atlas's path hits when it swings to its nearest point to the Sun at 1.36 astronomical units. Here, it faces the strongest solar warmth, hot enough to vaporize water ice and other frozen materials from its exterior. Its speed will top out at about 152,000 mph compared to the Sun. Regrettably for terrestrial watchers, this closest solar approach positions 3I Atlas on the Sun's opposite side from Earth, concealed by intense solar brightness and out of reach for Earth telescopes. Such placement poses hurdles, yet also opens doors for researchers. Key tools for viewing perihelion include probes at the L1 Lagrange point, about 1 million miles toward the Sun from Earth. SOHO and the Solar Dynamics Observatory can track 3I Atlas as it loops around the Sun via coronagraphs that obscure the Sun's glaring disk to spotlight dimmer features in the corona. Mars-based instruments will keep their prime vantage during this phase, with the planet's orbit aligning nearly at right angles to the Earth-Sun 3I Atlas line. This setup allows Mars craft to watch 3I Atlas amid its height of solar exposure, free from glare obstruction. The perihelion transit serves as a vital benchmark for rival ideas on 3I Atlas's makeup. For a true comet, the biggest coma growth and tail emergence should happen then. Lacking typical cometary signs or showing odd emission behaviors might back wilder ideas about its source. The intense solar warmth at perihelion will also challenge any man-made parts with severe heat strain. Substances unfit for space could break down dramatically, whereas advanced extraterrestrial tech could show up via surprising heat signals or managed venting. On December 19, 2025, Earth Proximity Assessment. Following perihelion, as 3I Atlas heads outward, it hits a key point on December 19 by coming about 170 million miles from Earth. At that range, beyond Mars's orbit, it becomes viewable by Earth's top observatories without posing any pull on our world. The December 19th viewing period is essential, as it marks the initial chance for in-depth Earth study of 3I Atlas post its solar closest approach. Any alterations in the changes in the object's look, makeup, or actions due to solar warming should become plainly apparent over this time frame. The James Webb Space Telescope will take a leading part in these examinations, leveraging its remarkable infrared detection to scrutinize the makeup of any emerging coma or tail. With its advanced spectroscopy tools, JWST can spot faint gases at levels well under what ground-based equipment can achieve, possibly uncovering rare substances or odd isotopic patterns that could suggest a manufactured source. The Vera C. Rubin Observatory, featuring its massive 4-meter main mirror and cutting-edge digital imaging system, will carry out thorough photometric surveillance to pick up even minor shifts in the object's luminosity or hue, which may signal continued operations or alterations to its form. These December viewings hold extra importance as they coincide with 3/3 Atlas traversing the solar system's ecliptic plane, heightening its encounters with solar wind and cosmic debris. Systems built to gather samples from solar system matter would likely operate at peak during this segment of the path. Terrestrial radio observatories will likewise target 3/3 Atlas in this window, hunting for radio signals that could point to functioning electronics. The object's position will suit radio studies ideally near enough for robust signal capture, yet distant enough to dodge disruptions from the Sun's radio output. On March 16, 2026, the Jupiter flyby. The prime scientific highlight of 3/3 Atlas's path through our solar system happens on March 16, 2026, as the object skims a mere 33 million miles over Jupiter's upper clouds. This near pass draws 3D Atlas deep into Jupiter's formidable magnetic zone, opening up exceptional chances for remote sensing and direct collection. NASA's Juno probe, now circling Jupiter, stands ready to perform in-depth scans of 3/3 Atlas amid the event. Juno's array of sensors, crafted to probe Jupiter's core makeup and magnetic properties, proves especially suited to notice any exchanges between the visitor and the planet's magnetic field. Navigating Jupiter's magnetic region will expose 3/3 Atlas to fierce radiation and particle strikes. Engineered defenses would require advanced protection to endure such conditions, whereas ordinary substances could show typical reactions to the radiation, detectable via Juno's gear. A key focus is whether Juno could snag dust grains released by 3/3 Atlas in the flyby. Jupiter's strong magnetic pull can hold onto charged particles, and Juno's particle analyzer might secure the first-ever human-collected bits of interstellar dust. The pull between 3/3 Atlas and Jupiter will also yield the ultimate precise gauge of the object's weight by closely following the gravitational tweak to its course. Experts can determine its mass with exceptional detail, clearing up lingering questions on its compactness and makeup. The Jupiter Pass marks the concluding big event in 3/3 Atlas's solar system trek. Beyond this, the object will head out on its ultimate hyperbolic path into the void between stars, slowly vanishing from sight as it slips past the grasp of our strongest scopes. After the Jupiter Pass and trailing scans, 3/3 Atlas will press on its curved route, ultimately exiting our solar system for good. The altered path post-flyby from Jupiter's pull will offer further details on its weight, and build based on the exact extent of this gravitational bending remains to be determined. Concluding views of 3I Atlas are expected to persist until the end of 2026, and perhaps extend into 2027, based on the comet's luminosity and the performance of upcoming advanced observatories. These final views hold special importance for spotting any enduring shifts in the comet's actions or features that could have escaped notice amid its short trip across the inner solar system. The full path of 3I Atlas's voyage offers a rare chance to examine an interstellar visitor across diverse scenarios, starting from its frigid, dormant phase on arrival, peaking with intense solar warmth at closest approach to the Sun, and then navigating Jupiter's harsh radiation field. Each segment of the path delivers distinct revelations about the comet's essential character. Regardless of whether 3I Atlas turns out to be a straightforward remnant from a distant stellar realm or an even more remarkable entity, its meticulously scheduled path across our solar system will supply researchers with observational records that experts will scrutinize and discuss for generations ahead. The path in itself has emerged as a key focus of investigation on par with the comet's material attributes, prompting deep inquiries into whether cosmic dynamics stem more from randomness or intentional structure. The dark forest theory, brought to prominence by Chinese sci-fi writer Liu Cixin in his renowned three-body problem series, delivers one of the most unsettling potential answers to the universe's eerie quietness. Also referred to as the dark forest hypothesis, this idea tackles the well-known Fermi paradox, the baffling clash between the strong likelihood of alien societies and the utter absence of proof for their presence. Drawing from an eerie analogy in Liu Cixin's narrative, the theory likens the cosmos to a shadowy woodland, with each society acting as a stealthy stalker, gliding among the shadows. As soon as one stalker gives away its position through any sound, it invites detection and swift eradication from fellow stalkers who regard it as a possible danger. Within this vast woodland of space, quietude ensures endurance, whereas exposure invites doom. At its core, the dark forest theory builds on a handful of core premises regarding societies and their encounters. It starts with the idea that staying alive drives every society above all else. Next, it claims that no society can reliably gauge the motives of those it comes across. Then, it contends that progress in technology naturally equips societies with the power to unleash destruction across stars. Lastly, it maintains that the immense gaps and lags in cosmic communication render amicable initial encounters all but unfeasible. Given these premises, a society spotting another confronts a dilemma with no easy resolution. It can't judge if the newfound society harbors friendly or aggressive aims. It can't bridge the communication gap owing to the enormous spans and prolonged waits in sending signals through space. It can't presume that a presently benign society won't turn aggressive as its tech evolves further. Thus, The rational course becomes a swift anticipatory assault, dubbed in the theory as a dark forest strike. This setup fosters a stellar deadlock akin to a Mexican standoff, where all societies stay mute and concealed, aware that being spotted by another probably spells total wipeout. Evolved societies craft ever more refined methods of concealment and evasion, all while staying alert for traces of rivals. The galaxy fills with covert observers, each wary of exposure, yet eager to uncover others first and avoid being uncovered. The dark forest theory's ramifications reach well past mere games of cosmic concealment among societies. It implies that highly developed ones would cultivate extensive networks of passive surveillance, employ advanced probes and observation outposts to collect data on possible dangers, all while ensuring their own invisibility. These scouting apparatuses must blend seamlessly into the environment to evade notice, disguising themselves as asteroids, comets, or harmless cosmic rubble. Within the framework of the 3I Atlas phenomenon, the dark forest hypothesis offers a lens for understanding the entity's peculiar features and path. Should this hypothesis hold true, our perception of an interstellar comet could in fact be a clever monitoring device crafted to examine our solar system under flawless guise as a commonplace celestial body. The dimensions of 3I Atlas take on added importance in this view. An object spanning 7 meters in width offers sufficient room to hide cutting-edge equipment, energy sources, and computing functions, all without altering its outward look as an ordinary comet. Its substantial weight would serve as robust protection from interstellar rays and solar warmth, safeguarding delicate components over the vast distances between stars. The path taken by 3ITA Atlas fits strikingly with the objectives of a dark forest scouting operation. The deliberate chain of close encounters with planets optimizes chances for data collection while reducing exposure through erratic movements. Reaching its closest solar approach on the Sun's opposite side from Earth establishes a built-in hiding phase, allowing any engineered features to function undetected by our premier detection tools. The unspoiled makeup observed in 3I Atlas might indicate authentic primordial substances carried from a remote stellar origin or an elaborate imitation aimed at deceiving spectral examinations. Sophisticated extraterrestrial tech could readily produce synthetic ices and organic materials bearing isotopic profiles that flawlessly imitate those from far-off star systems. In a dark forest context, the mission of 330 Atlas would center on thorough reconnaissance of our solar system and its likely residents. The device would evaluate our tech prowess, track our signals, scrutinize our world's atmospheres, and gauge if humanity poses an immediate or emerging risk to its makers. It could include refined passive detectors to pick up radio waves from Earth, probe our air for industrial markers, and survey our orbital installations for signs of progress. It may also feature probing tools that activate solely when screened from terrestrial views, like during the solar skim behind the Sun. The dark forest idea further accounts for why such a device would depart our system after a brief visit instead of lingering for ongoing study. Prolonged stays heighten discovery chances and could expose its constructed essence via minor irregularities in conduct. A one-time pass, by contrast, enables full intel acquisition while upholding impeccable natural cover as an interstellar wanderer. Skeptics of linking the dark forest hypothesis to actual celestial sightings highlight key flaws in this approach. The concept presumes uniform tech and social evolution across civilizations, overlooking the broad spectrum of potential developments. It further posits that cross-star annihilation is viable and superior to alternatives, a notion that's purely conjectural amid our scant grasp of superior tech. Moreover, it leans on game theory premises that might not hold in reality. Human ideas about evaluating dangers, handling risks, and planning strategies could prove entirely inapplicable to truly extraterrestrial minds shaped by distinct ecological and developmental forces. The dark forest hypothesis faces challenges in accounting for why a society sophisticated enough to deploy probes across the stars would view a technologically nascent group like modern humans as any sort of concern. Societies equipped for voyages between stars likely hold such vast technological edges that fledgling worlds akin to ours represent negligible dangers for eons to come. Even with these objections, the dark forest idea endures as persuasive, offering a unified rationale for the Fermi paradox alongside the peculiar traits of artifacts such as Three-Eye Atlas. It posits that the cosmos could overflow with sentient beings, yet these entities stay concealed through layers of advanced tech that render them nearly invisible to inferior societies. Regardless of whether the dark forest hypothesis truly captures the nature of cosmic societies, it acts as a useful lens for scrutinizing odd findings like Three-Eye Atlas. Contemplating that visitors from the stars may not invariably be mere cosmic debris encourages us to spot hints of sentience that could otherwise get brushed off as ordinary events. Moreover, the concept underscores the hazards tied to our escalating tech prowess and bolder footprint across the stars. Should the dark forest hold true, our broadcasts, ventures into space, and markers of progress may well have drawn unwelcome gazes from concealed watchers in the nearby stellar expanse. Dr. Abraham A.V. Loeb, the Frank B. Bede Jr. Professor of Science at Harvard University and past head of Harvard's Astronomy Department, stands out as a leading yet divisive figure in the quest for proof of alien intellect. His readiness to explore non-natural causes for bizarre celestial events has ignited fierce discussions among experts. This is especially evident in his examinations of wanderers from other systems, including Oumuamua and the recent Three-Eye Atlas. Loeb's foray into bold conjectures started with Oumuamua, the inaugural verified outsider to enter our solar domain. That elongated body displayed odd speeding up as it departed the sun, devoid of typical comet-like vapor releases, prompting most stargazers to offer unconventional natural accounts based on rare evaporation types or odd builds. Loeb, by contrast, pursued another path, proposing that Oumuamua's motions aligned with engineered design, particularly a solar sail driven by sunlight's push. This idea, outlined in his volume Extraterrestrial, the first sign of intelligent life beyond Earth, positioned Loeb as either a forward thinker defying norms or a esteemed researcher straying into overreach based on the viewer's stance. No matter the final truth of his Oumuamua theory, Loeb's method underscored the need to weigh every option amid truly puzzling sightings. Following the detection of Three-Eye Atlas, Loeb has again advanced ideas that contest standard views. In a study co-written with Dr. Carson Eel from the Harvard-Smithsonian Center for Astrophysics, Loeb contends that Three-Eye Atlas displays features aligning not just with man-made origins, but potentially better accounted for through engineered means. Instead of arising from natural processes, the core foundation of Loeb's Three-Eye Atlas theory hinges on the entity's exceptional dimensions compared to other interstellar travelers. Measuring 7 miles across, Three-Eye Atlas possesses sufficient scale to hide almost any type of cutting-edge equipment beneath a plausible facade resembling an ordinary comet. Loeb posits that such proportions strike an ideal balance for interstellar scouting missions, ample for housing complex machinery, yet not so immense as to scream artificial construction. In Loeb's examination, the dimensions of Three-Eye Atlas offer multiple benefits that an engineered interstellar device would greatly value. Firstly, its considerable bulk delivers superior protection against radiation, safeguarding delicate circuits over voyages that might span millions of years across stellar distances. Secondly, the generous internal space accommodates backup mechanisms and enduring energy supplies, capable of functioning across eons akin to geological eras. Thirdly, this magnitude permits the inclusion of thorough investigative tools for in-depth examination of destination star systems. Loeb further highlights the entity's elevated approach speed as a potential sign of engineered propulsion. Reaching 33 km in relation to the Sun, Three-Eye Atlas enters swifter than the majority of organic interstellar bodies, which generally show speeds from 20 to 30 kilometers. Though the gap appears modest, Loeb contends it may point to deliberate boosting that exceeds the boosts from mere natural gravitational assists. The backward path of Three-Eye Atlas plays a key role in Loeb's framework as well. Retrograde paths aren't rare among interstellar wanderers, but Lowe observes that this specific route creates prime setups for thorough solar system surveying. The reverse direction heightens the entity's engagements with local cosmic debris, and its particular tilt guarantees prime sighting opportunities from various worlds along the way. Of greatest note, Lowe stresses the unlikely odds of 3I Atlas's exact lineup of planetary close approaches. Its course, which positions it for Mars sightings, ideal solar warming near the Sun's closest point, a perfect pass by Earth for observation, and a final dip into Jupiter's magnetic field, displays a degree of accuracy that Lowe deems at odds with haphazard gravitational influences. Lowe draws comparisons to our own ventures in space, observing that 3I Atlas's path echoes routes crafted for human deep space explorers. Efforts such as Voyager and Pioneer showcased our drive to dispatch scouting craft outside the solar system, while simulations from NASA and similar bodies have mapped out efficient courses for imagined trips to neighboring stars. Numerous such projected routes mirror aspects of 3I Atlas's real path. Lowe's theory proposes that 3I Atlas could exemplify advanced archaeological astronomy, his phrase for spotting tech relics from alien societies via skywatching. In the same way that Earth-based digs uncover ancient societies from their physical traces, Lowe maintains that galactic powers might scatter tech clues detectable by scrutinizing odd celestial events. The disguise element in Lowe's idea tackles a frequent objection to notions of engineered beginnings. What motive would a superior society have for masking their inventions so elaborately? Lowe offers varied rationales, from moral principles against meddling with less developed worlds to tactical needs, like spying undetected to keep one's strengths and sources hidden. Lowe further tackles the makeup breakdown of 3I Atlas, suggesting that the identified water, ice, and organic materials could either be authentic ancient substances integrated into the probe's structure or clever biomimicry intended to deceive spectroscopic detection. He observes that a civilization advanced enough for interstellar journeys would almost certainly have the tech savvy to fabricate synthetic substances mimicking any specific chemical and isotopic profiles. The arrival of 3 Atlas in our solar system plays a key role in Lowe's examination. He highlights how the object's detection aligns with humanity's surge in technological progress, such as launching more advanced space observatories and initiating dedicated initiatives for interstellar messaging and exploration. This alignment may not be accidental if 3 Atlas serves as a scouting operation to evaluate our tech level. Lowe's theory goes further, proposing that 3I Atlas could be deliberately gathering samples of solar system substances for study. Its path carries it across zones abundant in interplanetary dust, solar wind debris, and various other elements that might yield detailed insights into our star system's makeup and history. Collecting such information would prove essential for any society pondering future engagements with our system. Detractors of Lowe's idea contend that he routinely prioritizes outlandish interpretations over simpler, everyday ones, a pattern that some peers believe erodes his standing in science. They stress that bold assertions demand robust proof, and while the odd traits of 3I Atlas are noteworthy, they fit within the spectrum of natural occurrences seen across the cosmos. Still, Lowe responds by emphasizing that true science demands exploring every feasible account for what we observe, even the awkward or improbable ones. He maintains that rejecting artificial sources from the start amounts to a human-centered prejudice that might blind us to real indicators of alien smarts. Lowe's handling of 3I Atlas echoes his wider views on hunting for extraterrestrial life. Instead of just anticipating clear signals like radio waves, he pushes for scouring astro data for tech traces that could uncover sophisticated societies. He calls this method space archaeology, which might spot signs of intellect without depending on deliberate outreach. If Lowe's idea holds true, its consequences for how we see our cosmic role would be immense. Verifying 3 Atlas as engineered tech would deliver the inaugural solid evidence that we're not solo in the universe. It would spark urgent inquiries into the motives and prowess of its makers, plus what other man-made items might already lurk undetected in our system. Even if Lowe's take on 3I Atlas doesn't pan out, his readiness to thoughtfully probe artificial causes for weird sky events fulfills a vital role in science. By challenging standard views, he compels fellow experts to bolster their premises more thoroughly and weigh options they'd typically overlook. Among the greatest enigmas of 3I Atlas lies in its omissions more than its revelations. As it nears the sun, skywatchers have ramped up hunts for the typical chemical markers expected from a natural comet this large under solar warmth. The puzzling lack of anticipated spectral signatures has emerged as a key enigma, upending traditional views on comet dynamics. Conventional comets, originating from the frigid outskirts of our solar system, consist of water ice, frozen carbon dioxide, methane, ammonia, and an array of organic substances. When these bodies draw nearer to the sun, solar energy triggers the direct vaporization of these fragile ices, forming the iconic coma and tail that render comets observable even to backyard stargazers. This activity commences subtly at around 5 to 6 astronomical units from the sun, then escalates sharply as the comet nears its closest solar approach. The particular vapors liberated in this vaporization yield unique spectral patterns, acting as identifiers for the comet's makeup. Among the easiest to spot are cyanogen, Cn, and diatomic carbon, C2, which generate prominent emission bands in the visible light range under the influence of solar UV rays. These compounds tend to emerge earliest, often becoming visible when the comet is still 3 to 4 astronomical units away from the sun. For something on the scale of 3I Atlas, boasting a rich supply of water ice and organics is verified by infrared analysis, the total absence of Cn and C2 signals is truly baffling. By the end of August 2025, with the object at about 2.5 astronomical units from the sun, precise spectral scans ought to have easily picked up these typical molecular outputs if they existed in standard quantities. Numerous facilities have carried out thorough hunts for these elusive markers, deploying ever more refined methods. The Very Large Telescope at the European Southern Observatory has allocated many hours to spectral tracking, zeroing in on the spectral zones where Cn and C2 peaks are anticipated. The Keck Observatory in Hawaii has utilized its cutting-edge spectrographs for comparable efforts. Findings across the board show no trace of the usual comet volatiles, even at fractions of typical concentrations. The Hubble Space Telescope has added UV spectral data, which is especially attuned to such molecular signals. Operating beyond Earth's atmosphere, Hubble avoids the distortions that could obscure faint lines in terrestrial setups. Even with dedicated sessions aimed at spotting initial comet-like outbursts, Hubble detected 0 signs of cyanogen or diatomic carbon near 3I Atlas. A few theories could account for this striking shortfall in standard comet indicators. The simplest suggests that 3I Atlas just hasn't ventured near enough to the sun yet for meaningful outgassing to kick in. Activation thresholds vary among comets based on their makeup and heat response. Some stay dormant until under 2 astronomical units, especially those with protective mantles built up from prior stellar flybys. Yet this idea struggles with 3I Atlas's profile. As an interstellar interloper, it has evaded prior solar warming, leaving its exterior fresh and responsive to sunlight favoring prompt activity over delay. Moreover, infrared evidence of water ice implies that portions of its volatiles are already exposed at its present solar distance. An alternative hypothesis points to inherent compositional variances between 3I Atlas and everyday solar system comets. Its extraterrestrial birthplace indicates formation amid a distinct chemical milieu. Potentially orbiting a star with varying metallicity or experiencing distinct temperature and pressure environments could lead to atypical molecular concentrations that fail to generate the usual cyanogen and diatomic carbon indicators. The isotopic examination of 3I Atlas has already shown notable deviations from materials in our solar system, especially in the deuterium to hydrogen proportions within its water ice. Comparable variations could appear in the carbon and nitrogen substances responsible for the absent spectroscopic features. If the organic components of the object possess atypical isotopic makeup, they could emit lines at marginally shifted wavelengths compared to predictions, complicating detection via conventional observation methods. A more unconventional hypothesis posits that the organics in 3 Atlas are incorporated into rare molecular configurations that resist decomposition into basic diatomic forms upon heating. Advanced societies equipped for interstellar journeys might utilize complex materials that preserve their form under circumstances that would degrade typical organic matter. These fabricated substances could vaporize in regulated manners, avoiding the erratic molecular outputs typical of natural cometary processes. The notion of deliberate concealment warrants attention as well. Should 3I Atlas be an engineered entity mimicking a natural comet, its designers may have foreseen scrutiny through spectroscopy to verify its legitimacy. Cutting-edge extraterrestrial tech could incorporate mechanisms to simulate authentic cometary outflows at key moments, while masking indicators of synthetic elements. Such a concealment setup might function through precise management of surface material vaporization, discharging water vapor and basic organics to form a plausible coma, all while inhibiting the development of intricate molecular types that could disclose the object's actual makeup. The substantial dimensions of 3 Atlas offer sufficient room to hide such intricate apparatuses. On the other hand, the lack of anticipated signatures could stem from the object's path and thermal background. In contrast to standard comets nearing the Sun from the frigid outer solar system, 3I Atlas has traversed interstellar voids for possibly millions of years. Throughout this voyage, exposure to cosmic rays and encounters with the interstellar medium may have transformed its surface chemistry, influencing its reaction to solar warmth. Though interstellar regions are largely vacant, they harbor faint traces of gas and dust, capable of slowly reshaping the chemistry on passing bodies. Bombardment by cosmic rays might fragment elaborate organic structures or forge atypical bonds that modify vaporization patterns. These effects could account for why 3I Atlas deviates from the behavior of comets that have lingered in our solar system since their origin. The missing cometary markers also prompt inquiries into when they might emerge. As 3I Atlas draws nearer to the Sun, solar warming will escalate sharply. Experts generally anticipate that upon reaching 2 astronomical units in late September 2025, unmistakable cometary behavior ought to manifest, should it arise at all. The closest solar approach in late October serves as the pivotal evaluation for every hypothesis regarding 3I Atlas's makeup and character. At 36 astronomical units from the Sun, the body will endure heat sufficient to vaporize nearly all volatile elements in its structure. Should conventional cometary markers not surface then, it would mark a truly extraordinary astronomical finding. Solar system astronomers, both on the ground and in orbit, stand ready to conduct thorough observations as the object nears its closest point to the Sun. The James Webb Space Telescope has set aside substantial slots for infrared observations that may pick up faint traces of gas release. Meanwhile, radio observatories are geared up to hunt for molecular signals undetectable in visible light. Solving the puzzle of the absent comet-like features will probably shape how much weight the scientific field gives to unconventional ideas about 3I Atlas's background and makeup. If no anticipated outflows show up as it draws closer to the Sun, that would mark a major oddity demanding answers, whereas the emergence of typical comet behavior could settle the enigma toward ordinary beginnings. That said, even detecting comet indicators might not fully clarify the object's true essence. Hypothetically, cutting-edge extraterrestrial tech could generate believable comet-like releases while hiding advanced mechanisms under a precisely designed shell. Astronomers face the tough job of telling real cosmic events apart from possible clever man-made imitations. Though the strange traits of 3I Atlas have fueled public curiosity and theories of artificial sources, nearly all expert astronomers hold steadfastly to the view that it's a natural, if peculiar, interstellar comet. This prevailing scientific agreement draws from years of studying solar system bodies, solid grasp of how planets form, and a rigorous method of assessing proof that leans toward everyday causes rather than wild ones. Occam's razor holds a key spot in the standard evaluation of 3I Atlas. This reasoning principle, which holds that the least complicated account fitting the data is usually right, solidly backs natural roots for the object. Sure, engineered creation might account for every quirky aspect of 3I Atlas, but that demands positing unknown advanced alien societies, intricate spacefaring tech, and reasons for scouting that are purely guessed at. In contrast, natural accounts, even if they involve rare conditions, depend solely on mechanisms and substances confirmed across the cosmos. Giant bodies can get flung out of their home systems via gravity tugs from giant planets or nearby stars. Untouched makeup can endure over vast interstellar travels. Rare odds, though slim, do happen now and then in a galaxy packed with hundreds of billions of stellar setups and endless chances for flukes. Dr. Alan Fitzsimmons from Queen's University Belfast, a top authority on minor solar system items, embodies the core scientific take on 3I Atlas. According to his review, its features, odd as they are, fit inside the spectrum of natural occurrences seen in our solar system and farther out. The scale, novel for interstellar visitors, isn't unheard of among comets overall. Plenty of comets here top 3I Atlas in width, such as Comet Hale-Bopp and the Centaur Churlo. The makeup of 3I Atlas, rich in pure water, ice, and organics, matches models for items born in the distant zones of foreign planetary setups. Models run on computers for planet building routinely indicate those areas yield bodies just like 3 Atlas, big, lightweight, loaded with volatiles, and barely heated. Mainstream astronomers tackle the unusual path of 3 Atlas, which has fueled considerable debate, by employing rigorous statistical evaluations and simulations of gravitational forces. Dr. Marco Macaulay, from the European Space Eyes Space Situational Awareness Program, explains that although the object's route stands out as statistically rare, it remains entirely feasible. In a vast galaxy boasting hundreds of billions of star systems and innumerable gravitational encounters, highly unlikely occurrences are bound to happen from time to time. Moreover, our view of the trajectory's rarity could be skewed by selection effects. We tend to focus more on celestial bodies that swing near Earth and other worlds, which makes these paths appear more frequent than they truly are. Trajectories that aren't as intriguing might zip through our solar system without notice, or with scant research interest, leading to a bias in observations that favors routes seeming deliberately crafted. The absence of typical comet-like emissions, which has baffled certain watchers, gets clarified by leading experts as a straightforward outcome of the body's heat exposure over time and its makeup. Dr. Geraint Jones at the Mullard Space Science Laboratory observes that comets start releasing gases at varying distances from the Sun based on their unique makeup and heat characteristics. Certain comets, especially ones with odd compositions or sturdy outer layers, stay dormant right up until they're nearly at the Sun. The fact that 3I Atlas hails from interstellar space could actually heighten the chances of such postponed activity. Bodies that have wandered interstellar voids for millions of years endure cosmic ray strikes and mingling with space dust, potentially reshaping their exteriors. Such changes might form protective coatings or tweak surface reactions, postponing the start of comet behavior. Experts in the field also highlight the confirmed presence of water, ice, and organic molecules in 3 Atlas as proof ruling out engineered creation. If it were a man-made scout, why bother embedding real interstellar substances complete with true isotopic markers? Building it from synthetic stuff that just looks natural from afar would be far easier. The isotopic patterns found in 3I Atlas, unlike those in our solar system, align perfectly with origins in another star's vicinity. Differences in a star's metal content, lifespan, and development history naturally yield varied isotopic mixes in solid objects. The particular markers seen in 3I Atlas fit models forecasting formations around stars, unlike our Sunday doctor. Aurorelli Gilbert-Lupuch of the Laboratoire d'Éologie de Lyon stresses that the actions of interstellar wanderers like 3I Atlas serve as vital checks on our theories of planet building and growth, Every fresh interstellar arrival lets us examine stuff shaped by alien settings, aiding in sharpening our ideas about how solar systems form across the galaxy. The scientific approach itself offers a structure for assessing ideas about 3, Atlas's possible engineered traits. Bold assertions demand robust proof, and though the body shows quirky features, all can be accounted for via ordinary natural mechanisms. Those suggesting a constructed source bear the onus of delivering proof that defies standard star science explanations. Leading researchers add that the engineered origin idea doesn't yield precise, verifiable forecasts distinct from natural accounts. A solid scientific theory needs to suggest detectable signs or tests that it is challenging to conclusively differentiate among rival theories. Assertions regarding concealed extraterrestrial tech or advanced masking mechanisms are by nature impossible to disprove, placing them beyond the scope of testable scientific inquiry. The rigorous peer review mechanism, central to advancing knowledge, has thoroughly examined assertions of 3I Atlas's manufactured origins. Although studies exploring the item's peculiar features have appeared in respected publications, experts in the field overwhelmingly prefer straightforward natural accounts over speculative, otherworldly ones. Such agreement stems not from rigidity, but from the collective insights of specialists who have devoted years to examining comparable celestial bodies and events. Initiatives by leading stargazers to engage the public highlight the need for critical thinking in assessing bold assertions. Dr. Michelle Bannister from the University of Canterbury observes that people's intrigue with possible cosmic travelers is relatable and beneficial for sparking enthusiasm in the stars, yet it should pair with strict commitment to evidentiary norms in science. Astronomy's past offers many instances where enigmatic occurrences were ultimately clarified by ordinary mechanisms. Pulsars, at first thought to be signals from aliens, were revealed as swiftly spinning neutron stars. Gamma-ray bursts, once eyed for engineered sources, emerged as some of the cosmos's most powerful innate events. The experts' wariness toward 3 Atlas draws from these cases and many more. That said, conventional researchers admit their everyday interpretations of 3I Atlas's traits fall short of full resolution or total conviction. Its dimensions, path, and makeup pose real enigmas demanding further investigation and perhaps innovative conceptual models. The lack of anticipated comet-like traces, though not entirely novel, defies existing theories. Admitting this gap does not endorse ideas of engineered beginnings. Instead, it highlights gaps in our grasp of spacefarers and comet-like actions. Knowledge in science builds via methodical evidence gathering and steady theoretical polishing, rather than bold jumps to outlandish ideas. The current monitoring effort for 3I Atlas should eventually yield the data to settle debates on its essence. As it nears its closest solar approach and faces peak sunlight, the item's actions could align with typical comet patterns or show oddities calling for unconventional interpretations. Researchers stand ready for any result, upholding measured doubt toward outsized claims. The discourse around 3I Atlas exemplifies the productive clash of curiosity and caution that propels discovery. Though the majority of skywatchers lean toward mundane origins, the exchange has spurred deeper probes into the item's properties and raised key inquiries on detecting true extraterrestrial signals in cosmic records. The Tale of One Eye. Oumuamua, our solar system's inaugural verified wanderer from afar, offers vital background for grasping ongoing talks on 3I Atlas and the hurdles in decoding unusual sky sightings. Unearthed on October 19, 2017, by stargazer Robert Warwick via the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii. Oumuamua right away posed riddles that kept testing standard views on such interstellar travelers. The finding routine at the outset. Pan-STARRS, built to sweep the heavens for astronomers, first spotted a dim, shifting body that seemed like yet another near-Earth asteroid needing routine monitoring. It took multiple evenings of close monitoring before experts understood they had encountered something remarkable, an entity following a hyperbolic path that had come from beyond our solar system. The Pan-STARRS team, working with Hawaiian linguists, selected the name Oumuamua, which translates to messenger from afar arriving first in Hawaiian. This evocative label turned out to be fitting, as the visitor ultimately offered insights into interstellar environments and upended our ideas about what objects from distant stars could resemble. Early sightings of Oumuamua showed it differed vastly from anything known in our solar system. Photometric data indicated a highly stretched form, with a length-to-width aspect of about 10.1, evoking a stellar cigar or pin rather than the usual rounded profiles of asteroids or comet cores. Such odd proportions quickly ignited curiosity and debate over its beginnings and how it formed. Even stranger were its surface traits. The body displayed exceptional brightness, with an albedo around tenfold that of ordinary comets and asteroids. This glossy sheen, paired with a rusty hue akin to items in the outer solar system, pointed to an makeup distinct from standard cosmic debris. Explaining the strong reflectivity posed a challenge, since space objects typically acquire murky carbon-rich coatings from prolonged exposure to cosmic rays and particles. The biggest enigma, though, was Oumuamua's lack of cometary behavior, which scientists anticipated from an interstellar interloper. As it neared and swung around the sun, no hazy envelope or tail emerged, no gases were spotted, and even top-tier telescopes detected no dust release. For something with Oumuamua's expected makeup and path, this total absence of activity broke all precedents. The puzzle grew when precise position data uncovered a slight, yet consistent, non-gravitational push propelling it from the sun. This boost exceeded what sunlight alone could cause, yet no visible venting appeared to drive it like a rocket via evaporating ices. The push aligned with the exact formula tied to distance from the sun, fading as it receded, just as radiation pressure would predict. But its strength was way beyond what Oumuamua's calculated dimensions and weight could account for. Dr. Marco Micheli from ESA's Space Situational Awareness Program headed the group that uncovered this odd motion via meticulous review of data from various telescopes. The effect was faint, about 5×10⁶ Menasiur-2, yet steady and beyond error margins. Their work, detailed in a June 2018 Nature paper, sparked a range of theories for Oumuamua's odd path. Most researchers favored natural causes for the baffling thrust. The top idea was that faint, undetectable venting was at play, perhaps hydrogen from sublimating water ice, too subtle for spectra to catch, but enough to generate the needed momentum. Other ideas pointed to exotic materials in Oumuamua's structure that might scientists have sought to account for its remarkable reflectivity and peculiar acceleration. Certain experts posited that the entity could be a chunk of solid hydrogen created in the frigid conditions of interstellar space. Alternative theories put forward the idea that it might be made up of rare ices or organic substances exhibiting odd heat characteristics. The most thorough natural hypothesis, crafted by Dr. Daryl Seligman from Yale University along with colleagues, portrayed Oumuamua as a dark comet and interstellar body that had shed much of its volatile components after repeated near-star encounters, resulting in a remnant core that could undergo modest outgassing when exposed to strong solar warmth. This framework accounted for the absence of evident cometary features, as well as the faint acceleration, though it demanded an intricate backstory of thermal evolution and gas release. Yet, it was Dr. Avi Low of Harvard University who advanced the boldest and most divisive theory regarding Oumuam's odd traits. In a collaborative study with Dr. Bialy Loeb, he contended that the object's pronounced elongation, elevated reflectivity, and propulsion from solar radiation pressure aligned with deliberate artificial design. In particular, a solar sail produced by an advanced alien society. Lowe's solar sail concept resolved several puzzles at once. The stretched shape might stem from design needs for optimal sail performance. The strong reflectivity proved vital for amplifying the impact of radiation pressure. The exact link between its speed-up and proximity to the sun fit models of solar sail dynamics. Above all, this idea clarified the presence of outgassing-like acceleration without any observable gas outflows. The astronomy field responded to Low's idea with rapid and mostly dismissive feedback. Detractors maintained that bold assertions demand robust proof and that Oumuamua's quirks, though striking, remained explainable via ordinary mechanisms without resorting to extraterrestrial engineering. Rigorous peer review grilled Lowe's submissions, and although they appeared in respected publications, the majority of researchers stayed skeptical. NASA's Spitzer Space Telescope contributed significantly to the Oumuamua probe through its null findings, which carried nearly as much weight as confirmations. The telescope's finely tuned infrared scans overlooked the object on its outward path, setting boundaries on its dimensions and heat output that refined possible explanations. These readings indicated that Oumuamua was more compact than first thought and emitted less heat than a standard asteroid or comet would. The lack of Spitzer detection also bolstered unconventional ideas about the object's makeup. Should Oumuamua truly be a slender mirror-like solar sail, its diminutive size and low temperature could render it invisible to infrared instruments, matching the Spitzer data. That said, the outcome equally backed everyday theories tied to atypical makeup or form. As Oumuamua pressed onward into the outer solar system, it dimmed past the reach of the finest observatories, bequeathing a trove of data, yet no clear resolution to its origins. Its swift traverse of our cosmic neighborhood showcased the prowess of contemporary stargazing while underscoring the challenges of probing transients that offer just momentary glimpses. Insights from Oumuamua have since enriched efforts to examine later interstellar intruders such as 3I Atlas. Researchers have refined spotting methods, conceptual models, and processing tools now in use for this latest arrival. Crucially, the Oumuamua saga underscored the urgency for rapid responsibilities, and extensive monitoring efforts proved essential in handling fleeting interstellar visitors. The discussions around Oumuam set vital benchmarks for assessing assertions of possible alien technology. The research community's prudent stance toward Lowe's idea highlighted the value of exploring every feasible explanation, alongside the demand for strict proof when scrutinizing bold assertions. Reflecting on the Oumuamua incident from a 2025 viewpoint reveals several crucial lessons that shape today's conversations about 3I Atlas. For one, such cosmic wanderers might display traits that defy standard interpretations without implying artificial origins. Additionally, the lack of anticipated features, such as comet-like outgassing, holds as much scientific weight as their occurrence. Moreover, probabilistic claims regarding unusual attributes require thorough review, accounting for detection biases and viewing constraints. The Oumuamua saga underscored the benefits of sustaining various rival theories during scrutiny and examination phases. Although the majority of experts leaned toward organic origins in the end, the persistent discourse spurred deeper probes into the visitor's attributes and uncovered findings that could have easily been missed. Above all, Oumuamua illustrated how the cosmos retains astonishing elements that test our conceptual models. Its distinctive mix of features, extreme slenderness, elevated brightness, odd propulsion, and no signs of cometary behavior hadn't been foreseen by any simulations of interstellar travelers. This sobering episode served as a prompt to stargazers that reality frequently surpasses the limits of our creative visions and analytical constructs. The innovations from the Oumuamua probe keep aiding ongoing inquiries. Enhanced positioning methods, refined spectral analysis tools, and superior predictive frameworks all support the in-depth examination of 3I Atlas. The framework of global teamwork and swift information exchange, built amid the Oumuamua effort, has smoothly transferred to this latest solar system intruder. As 3I Atlas proceeds on its path across our stellar neighborhood, experts tackle its analysis with the thrill of revelation tempered by the tough-earned knowledge from the Oumuamua encounter. Regardless of whether this present guest turns out to be a commonplace body or an unusual anomaly, the takeaways from our inaugural, verified interstellar arrival guarantee that vital sightings and analyses won't escape notice. The tale of Oumuamua acts as a nudge that existence is infinitely more bizarre and marvelous than we typically envision, and that astronomy's forthcoming breakthrough could show up abruptly, masked as merely another dim speck drifting amid the constellations. Following Oumuamua detection and the intriguing enigmas it sparked, the worldwide aerospace network started contemplating bold initiatives to pursue and examine interstellar drifters. Among the boldest was Project Lyra, a conceptual endeavor aimed at overtaking Oumuamua for close-up, on-site scrutiny of humankind's debut, authenticated interstellar arrival. Project Lyra arose from joint efforts by the European Space A's forward-thinking group and experts from global organizations. Its title, drawn from the LRA star group, from which Oumuamua's path hinted at a starting point, captured the lyrical and empirical essence of launching humanity's initial pursuit across the stars. The engineering hurdles for Project Lyra were immense, by-the-moment dedicated planning. Planning for the mission started back in 2018, when Oumuamua was already speeding away from the Sun at velocities surpassing 26 kilometers per second. Intercepting an object traveling at those incredible speeds demanded spacecraft innovations that stretched the limits of today's engineering, such as cutting-edge propulsion methods, intricate guidance software, and self-reliant systems for vast interstellar voyages. Initial path evaluations showed that a standard chemical rocket trip to Oumuamua was out of reach with present-day tech. The power needed to sync up with the object's pace went beyond what any existing booster could deliver. Even leveraging slingshot maneuvers from several planets, a probe would have to manage speed adjustments well outside the grasp of conventional engines. As a result, the Project Lyra group zeroed in on forward-thinking drive ideas like light sails, electric ion engines, and speculative nuclear fusion thrusters. In the end, solar-powered electric propulsion stood out as the best feasible choice in the short term, relying on high-efficiency ion engines fueled by expansive solar panels to steadily build up a probe's momentum across years or even decades. Although the journey would stretch out enormously before arriving at the destination, the wealth of knowledge from hands-on examination of extrasolar matter made the prolonged schedule worthwhile. Dr. Andreas Hein, from the Initiative for Interstellar Studies, directed in-depth viability assessments that outlined possible frameworks for missions to Oumuamua. Those analyses indicated that, even under the rosiest projections for upcoming drive advancements, a launch in the early 2020s wouldn't catch up to the object before the late 2040s or early 2050s. At that point, Oumuamua would have drifted so distant from the Sun that sunlight would barely suffice for power, necessitating atomic energy supplies to keep the probe running. The gear for a Project Lyra endeavor would have to endure dependably for decades amid the unforgiving conditions of deep space. High-tech analyzers, cameras, and material-gathering tools would all require impeccable performance following prolonged exposure to radiation from cosmic rays, wild swings in temperature, and ongoing strain from persistent thrust. In essence, the endeavor would demand pioneering tech for genuine star-spanning travel well ahead of its time. Linking up with a Project Lyra probe would bring its own hurdles. Upon arrival at Oumuamua, the craft would sit hundreds of times more remote from our planet than any prior deep space venture. Wireless transmissions would require hours to bridge the gap between ground control and the vessel, ruling out instant oversight and calling for extraordinary onboard independence. The protective barriers needed to withstand a near flyby of an extrasolar visitor also created major design obstacles. Given the intense closing speeds, even minuscule specks of debris could act like lethal bullets. The vessel would demand clever armor setups to safeguard sensitive equipment from such rapid collisions, all while enabling the capture and study of bits from the object itself. Even with these daunting obstacles, Project Lyra sparked considerable buzz in the aerospace world. The European Space Agency wove interstellar visitor pursuits into their extended strategic outlines. NASA's Jet Propulsion Laboratory ran early probes into the necessary innovations for these kinds of operations. Meanwhile, commercial space firms started weighing how their growing expertise could aid in pushing toward the stars. The spotting of 3/3 Atlas in July 2025 has utterly reshaped the prospects for chasing interstellar wanderers. In contrast to Oumuamua, which turned up on its way out, 3I Atlas was picked up as it was still heading toward the Sun. This early heads-up offers. This remarkable interstellar object opens up extraordinary possibilities for mission design and even quick reaction expeditions leveraging current or soon-to-arrive technologies. Dr. Petra Pokorny, from NASA's Goddard Space Flight Center, has spearheaded initial investigations into feasible expeditions targeting 3I Atlas. Drawing on insights gained from Project Lyra preparations, the prolonged monitoring phase prior to 3I Atlas's perihelion passage enables precise path adjustments, thorough expedition strategies, and possibly the development and deployment of specialized probes tailored precisely to this event. The path of 3I Atlas, featuring its meticulously timed series of gravitational assists from planets, offers distinctive prospects for probe deployments. A spacecraft dispatched to meet the intruder near its Mars encounter might perform in-depth examinations while the cosmic wanderer remains comparatively dormant. As another option, an expedition aimed at linking up with 3I Atlas amid its Jupiter rendezvous could harness the gas giant's immense gravity for path corrections and prolonged scrutiny sessions. The substantial dimensions of 3I Atlas relative to Oumuamua alter the demands and potentials of such ventures. Although its 7 kilometers width poses hurdles for full-surface charting and examination, it also establishes a reliable base for sustained monitoring and perhaps even landing activities. A probe fitted with descent modules or drills might execute thorough underground probes unattainable on tinier bodies. Gathering samples from 3I Atlas could mark the pinnacle of discovery in cosmic research history. Hands-on study of untouched extrasolar substances might yield groundbreaking knowledge about world-building mechanisms around distant suns, the spread of carbon-based molecules across the cosmos, and maybe traces of extraterrestrial biology from afar. The engineering demands for a 3I Atlas expedition, though demanding, prove far more attainable than Project Lyra's. Its inbound route supports standard liftoff periods and travel durations in years, not decades. Proven electric thrusters might facilitate intercept operations, whereas cutting-edge light sails could support drawn-out surveillance and material retrieval functions. Global collaboration stands as crucial for any thorough 3I Atlas endeavor. No one space organization holds every tool and asset needed for this bold pursuit. It would probably draw inputs from NASA, ESA, JAXA, and further entities, plus possible roles for innovative private firms boasting superior expertise. The schedule for a 3I Atlas operation hinges largely on its scope and worldwide dedication. A basic pass-by probe with off-the-shelf gear might lift off in 2 to 3 years, reaching the goal amid its outward path in the late 2020s. Elaborate intercept and retrieval operations would demand extended preparation, but could still connect with the target inside viable signal and guidance limits. The payloads for a 3I Atlas operation would expand on generations of know-how from comet and rock investigations. Sophisticated analyzers able to spot faint elements and odd atomic signatures would prove vital for uncovering the body's authentic makeup. Sharp imaging gear might uncover terrain traits and build qualities that could separate innate from engineered sources. Above all, a 3I Atlas operation might incorporate tools crafted to hunt for evidence of deliberate fabrication or devices. Magnetometers could identify anomalous magnetic signatures, potentially signaling electronic devices could be detected. Instruments like radar sounders might delineate subsurface features, pinpointing cavities or regular shapes that defy typical geological origins. Chemical sensors would probe for synthetic substances or elements absent from earthly environments. Insights gained from an in-depth probe of 3I Atlas hold the power to reshape our comprehension of humanity's cosmic role entirely. Verifying the body as genuine extrasolar matter would yield groundbreaking knowledge on how planets assemble and develop across the Milky Way. Uncovering engineered elements or advanced tech would mark the greatest breakthrough in scientific annals. With global teams now contemplating interception paths for 3I Atlas, insights from the Lyra initiative offer crucial advice on sidestepping errors and optimizing research yields. Vital elements for Triumph include global partnerships, tech advancements, and adaptable flight designs. Regardless of whether a 3i Atlas venture secures backing or clearance, the preparatory work alone spurs innovation in technology and cross-border collaboration, aiding subsequent ventures into space. Tools crafted for probing interstellar wanderers will pave the way for authentic voyages beyond our stars, unlocking fresh realms for human outreach and revelation. The time frame for pursuing 3i Atlas encounters will narrow as the entity ventures deeper into the solar periphery and further out. Choices in the near future will decide if we grasp this rare chance to examine samples from a distant stellar realm firsthand, or merely observe as our latest extrasolar guest slips away into the void, carrying its enigmas along. Spotting 3 verified interstellar intruders in under 10 years grants stargazers a rare chance to examine and differentiate traits of these alien system envoys. Every one Muamua Boris and the current 3. Atlas displays unique traits that together outline the spectrum of interstellar oddities we anticipate, while underscoring the singular qualities rendering each a treasure for study. 2. Boris, spotted by hobbyist Sky. The core of Boris, measured at about 1 kilometer across, proved far smaller than 3i Atlas, yet it aligned more closely with the dimensions of ordinary comets, its nearly round form and leisurely spin cycle of around 7. 3 hours pointed to origins via typical build-up mechanisms in the distant zones of its original star system. When examining Borisov alongside 3i Atlas, notable parallels surfaced that could highlight shared traits among wanderers from other stars. Both feature makeup primarily of water ice and organic substances. Each displays signs of emerging in chilly outskirts of star systems, and each carries isotope markers that set them apart from stuff in our own solar system. Such overlaps imply that sizable frozen bodies might rank as the most frequent ejecta flung into the void between stars as star systems develop. The contrasts between Boris and 3i Atlas offer valuable lessons too. The vast-scale Gap 3i Atlas, holding about 1,000 times the volume of Boris, hints at varying origins or launch methods, whereas items like Boris could stem from gravitational flings of minor comets amid planetary shifts. A behemoth like 3i Atlas probably demands far more intense upheavals, like brushes with other stars or the breakup of major worlds. Patterns of comet-like behavior also vary sharply between these two. Borisov started displaying a visible coma at roughly 6 AU from the Sun, standard for ice-rich comets driven by water. 3i Atlas, for all its greater bulk and likely larger reserves of volatiles, has revealed no obvious comet activity by late August 2025, despite nearing ranges where significant vapor release would be anticipated. Oumuamua stands out as the wildest case of odd conduct among these cosmic intruders. Its absence of any observable comet traits, paired with puzzling extra pushes beyond gravity, separates it from both Boris and 3i Atlas. The body's extreme stretch shape, bright surface, and compact dimensions form a profile that's tough to fit into usual theories of how natural bodies form. Looking at all 3 together uncovers intriguing trends in how they were found and the chances for watching them. Oumuamua turned up on its way out, granting just a short spell for in-depth scrutiny before it slipped past our view. Borisov appeared on its inbound leg, enabling broad observation efforts, though the time frame stayed constrained. 3i Atlas, spotted heading in, delivers the extended viewing span and prime shot at thorough analysis. Their paths through our solar system differ in compelling ways as well. Oumuamua's route past the inner planet stayed fairly direct, dodging any standout close shaves with worlds. Borisov's course swung nearer to the Sun than 3i Atlas is set to get, yet it skipped the carefully timed lineup of planetary swings that marks this latest guest's route. In terms of dimensions, the trio covers a huge spectrum that underscores the variety in interstellar debris. Oumuamua, stretching to about 400 meters, embodies the tiniest detectable class of such visitors. Boris, with its 1 kilometer width, matches the scale of everyday comets from our system's fringes. Midori. Atlas, spanning 7 meters, introduces a fresh category of enormous interstellar bodies that might be uncommon yet priceless for science upon discovery. Breakdowns of their makeup shed light on the chemical range in interstellar stuff. Oumuamua's makeup stays mostly a mystery, thanks to no vapor release in the short viewing period. Window. Borisov displayed unmistakable signs of water ice, carbon monoxide, and organic compounds featuring atypical isotopic ratios. The 3I atlas seems to harbor unspoiled water ice, along with intricate organic substances that could have endured for billions of years. These variations in makeup might stem from origins in distinct stellar environments or varying periods within the galaxy's timeline. Oumuamua peculiar traits could point to development amid harsh circumstances or in settings divergent from standard planetary setups. Borisov's makeup implies creation in a chilly, carbon-abundant zone, orbiting a star whose metal content differs from our Sun's. 3I Atlas looks to retain substances from a star system boasting greater concentrations of heavy elements and an earlier formation era. The heat-related features of these three entities differ markedly as well. Oumuamua exhibited odd thermal traits that fueled discussions on its makeup and build. Boris showed heat patterns fully aligned with ordinary comet stuff. 3. I-Atlas has seen little thermal scrutiny so far, since it hasn't neared the Sun closely enough for notable warming. Detection techniques for each of these bodies have advanced sharply with every find. Oumuamua was first thought to be an asteroid and only pegged as interstellar after a few nights of tracking. Boris raised suspicions of interstellar routes right away from its odd path, with verification arriving swiftly. 3I Atlas got flagged as a possible interstellar traveler just days after spotting, thanks to upgrades in automated spotting and review tools. The knowledge gained from examining each has differed widely. Oumuamua sparked massive scientific buzz and arguments, but yielded few firm conclusions on its essence or beginnings. Borisov delivered solid clues on interstellar comet makeup and actions, while sparking fresh inquiries into the variety of planet-building mechanisms. 3I Atlas holds out hope for the fullest dataset to date on any interstellar wanderer. Moving ahead, contrasting these three arrivals offers key insights for decoding upcoming interstellar finds. The spectrum of dimensions, makeups, and actions seen hints that the space between stars holds a varied array of items with diverse sources and features. Certain ones, such as Boris, could stand as simple cases of regular comet material. Others, like Oumuamua and perhaps 3I Atlas, might upend traditional views and demand fresh conceptual models. The sequence from Oumuamua via Borisov to 3I Atlas also highlights the swift strides in our capacity to probe interstellar objects. Each following guest has faced scrutiny from sharper tools, deeper conceptual grasp, and broader watching efforts. This evolution in tech and approaches guarantees that coming interstellar guests will undergo examination with unmatched thoroughness and accuracy. The trio of verified interstellar objects lays the groundwork for a stats-based overview of such populations. Though just 3 items make for a tiny batch, they already hint at substantial variety in the kinds of stuff journeying across star systems. Later finds will steadily expand this stats base, paving the way for stronger deductions on how often these visitors appear, their traits, and their routes. Above all, perhaps, the matchup of Oumuamua Boris and 3I Atlas shows that every interstellar arrival is probably distinct in certain ways, calling for tailored examination methods and flexible takes on the data gathered. The universe appears to be far interstellar objects exhibit a greater variety and unexpected qualities than what current theoretical frameworks anticipate, guaranteeing that every fresh find from beyond our solar system will offer distinct perspectives on the mechanisms of planet building, star development, and the universal forces linking stellar groups across the Milky Way. The path taken by 3I Atlas as it traverses our solar system poses a numerical enigma that defies standard notions of orbital physics and sparks deep inquiries into the balance between randomness and purpose in celestial events. Upon initial computations by stargazers of the exact route this 7m wide interloper would trace while navigating the inner reaches of our system, the odds-defying elements were so staggering that they necessitated exploring ideas outside mere haphazard gravitational influences. At the heart of scientists' deliberations lies the core dilemma. Does the striking exactness of 3I Atlas's course signify a rare fluke or proof of deliberate engineering? Such a debate delves into profound philosophical territory regarding our ability to separate organic occurrences from engineered artifacts, especially in the context of entities that could embody technology vastly superior to humanity's. Dr. Alan Jackson from the University of Toronto's Centre for Planetary Sciences has spearheaded the thoroughgoing probabilistic examination of 33 Atlas's path, employing Monte Carlo methods to assess the likelihood of such a trajectory arising from unguided mechanisms alone. His study accounts for the incoming direction and speed, the tilt of the orbit, closeness to planets during flybys, and synchronization with Earth's yearly circuit. The evaluation starts by examining 3I, Atlas's entry direction and pace. It originates from the Draco constellation, bearing a defined speed profile that sets it on a backward tracing path tilted at 162 relative to our planet's orbital plane. Although backward paths aren't rare among extrasolar visitors, this exact angle ensures the body remains observable from Earth for its full journey through the central solar zone. According to Jackson's findings, the odds of this precise tilt happening accidentally stand at about 0.6. Though slim, this figure by itself fails to provide strong grounds for suspecting artificial involvement. Yet, integrating it with further path features yields a compounded likelihood that's markedly more telling. The lineup of planetary close approaches forms the trajectory's most probabilistically demanding feature. 3I Atlas is set to skim within 18 million miles of Mars on October 3rd. It will hit its nearest point to the Sun at exactly N1:36 AU on October 29th. Then, it draws within 170 million miles of Earth on December 19th, before brushing Jupiter at 33 million miles on March 16, 2026. Every such proximity and schedule imposes a unique set of orbital requirements that align concurrently. Assessing the odds for the Mars flyby involves factoring in the positional and chronological harmony needed for the intruder to meet the red planet at its location. With Mars's 687-day cycle and the complex spatial layout, the chance of an arbitrary interstellar body pulling off this distance and moment is around 0.8. The Sun closest point schedule and range introduce further limitations. The body achieves its minimal solar distance right when it's obscured by the Sun as viewed from Earth, setting up ideal scenarios for undetected monitoring or activity. The likelihood of this exact timing by pure chance hovers at about 1.2. The Earth close pass in December layers on yet more unlikelihood. That 170 million mile gap positions 33 Atlas perfectly for in-depth scrutiny via orbital telescopes. Telescopes can observe it without causing any gravitational disturbances to Earth's path around the Sun. This moment aligns perfectly with the best viewing angles from observatories in the Northern Hemisphere. Together, these factors result in a roughly 0.4 chance of happening by pure coincidence. The close pass by Jupiter stands out as the most intricate in terms of geometry and the least likely statistically across the whole path. Coming within 3 million kilometers puts 33 Atlas right inside Jupiter's magnetosphere, where energetic particles and magnetic forces might affect any onboard artificial equipment. This flyby occurs just as Jupiter is ideally placed for scrutiny from ground-based telescopes on Earth. The odds of such a rendezvous happening at random are figured to be under 0.1. Factoring in every element of the route at once, Jackson's calculations produce an overall likelihood of about 0.05, or 1 in 20,000. In many scientific disciplines, this level of improbability would signal compelling proof of something deliberate rather than chance. That said, evaluating stats for uncommon occurrences demands vigilance against selection biases and viewing prejudices that could exaggerate how unlikely things appear. Dr. Sarah Greenstreet from the University of Washington has spearheaded work to unpack these distortions when it comes to spotting and examining interstellar visitors. Greenstreet highlights how our discovery techniques inherently prefer objects whose paths swing near Earth and other worlds. Those zipping through the distant solar system sans close planetary brushes are much harder to spot and probe, fostering a bias toward routes that look unusually captivating. Such filtering could make meticulously planned orbits appear more frequent than they truly are. Moreover, our innate drive to spot designs in chaos termed apophenia can shape how we read these path stats. Faced with a particular chain of happenings, one can derive tiny probabilities by zeroing in on exact specifics, all while overlooking the multitude of other scenarios that might have struck us as equally astonishing had they unfolded. Debating purpose against fluke also hinges on guesses about the aims and prowess of any imagined extraterrestrial tech. Should 3-2 Atlas embody engineering from a sophisticated society, what goals could this route fulfill? Examining its features reveals a few potential aims. A scouting probe aimed at surveying our solar system's key worlds would gain hugely from the precise lineup of approaches shown by 3-2 Atlas. The Mars swing-by offers up-close views of a rocky world with air and land traits hinting at life potential. The Sun's closest approach permits in-depth probing of our star's properties, plus gathering samples of solar wind. The Earth Pass allows thorough scanning of our world's air layer, magnetic shield, and hints of advanced life forms. The Jupiter swing-by grants entry to the system's biggest planetary magnetic zone and its intricate moon network. Plus, each pass aligns with prime windows for data collection. The Mars one unfolds under dawn lighting that boosts clarity of the atmosphere. The Sun's perihelion hits during a stretch when the object stays out of sight from Earth observers, perhaps enabling discrete activities. The Earth one lines up with superior sight lines for fine-grained surface mapping. The Jupiter one unfolds as the gas giant sits favorably for Earth telescopes to track the event. Another viewpoint. This hypothesis indicates that the path could be optimized for gathering samples from solar system debris instead of focusing on planetary surveys. As 3-Eye Atlas travels across various zones in interplanetary space, it runs into diverse concentrations of dust, ionized particles, and magnetic influences, offering detailed insights into the characteristics of our stellar neighborhood. The backward-facing orbit boosts the object's speed relative to this debris, which might improve the rate of material capture. The orbital physics involved reveal a deep grasp of how paths in space behave. Should the route prove to be engineered, interactions with planets would subtly adjust the object's course via gravity, refining it for future flybys. Achieving this kind of gravitational pinball demands exact starting parameters and expert path design to pull off effectively. Opponents of the deliberate creation theory claim that the probability calculations overlook the enormous array of routes interstellar visitors could take. Given the infinite variety of three-dimensional paths and endless timing options, even the rarest occurrences are bound to happen now and then. The seeming importance of 3-Eye Atlas's path may stem from our innate habit of reading profound significance into any odd setup we happen to notice. Moreover, the idea that engineered objects would always stick to the most efficient routes could be misguided. Highly evolved societies might operate under unique goals, limitations, or logics that clash with what we humans anticipate. From our viewpoint, something ideal might hold no value or even work against the aims of a truly foreign mind. The clash between true rarity and mere chance highlights wider difficulties in separating organic from manufactured events, especially with tech that outstrips our own grasp. Classic SETI efforts target clear signs of intent, such as radio waves or laser beams. Yet, super-advanced groups could use scouting techniques so refined that they blend seamlessly with cosmic norms. Such a scenario prompts us to wonder what kind of proof would seal the case for an engineered source in something like 3-Eye Atlas. Odds-defying stats, though intriguing, fall short without more. Spotting synthetic substances, structured shapes, or functioning components would offer far stronger clues. Still, a civilization capable of building star-spanning scouts might also master the art of hiding blatant traces. Settling the puzzle of 3-Eye Atlas's route will hinge on ongoing monitoring as it sticks to its forecasted track. Should it stray from pure gravity's pull via maneuvers or other oddities, those shifts would signal engineered controls. On the flip side, if the path adheres strictly to orbital rules with no mysteries, an organic source gains ground, improbabilities notwithstanding. The probability breakdown of 3-Eye Atlas's route marks a fresh edge in hunting for alien minds, emphasizing faint clues over blatant broadcasts. Regardless of whether it uncovers real traces of extraterrestrial guests or just exposes our knack for spotting designs in chaos, it has reshaped how we view valuable clues in the quest for cosmic companions. The 3i Atlas event has compelled the SETI field to challenge core beliefs regarding the ways alien life could appear in our part of the universe. For more than 60 years, SETI investigations have mainly concentrated on spotting radio waves, light bursts, and various clear man-made broadcasts from remote societies. The notion that extraterrestrial minds could arrive in our solar system as advanced scouting devices signals a major transformation that might redefine the discipline entirely. Dr. Jill Tarda, ex-head of the SETI Institute and a trailblazer in hunting for alien intelligence, recognizes that 3i Atlas has broadened our perspective on sensing methods we previously overlooked. Conventional SETI methods presume that evolved societies would seek to reveal themselves via noticeable signals. Yet, a scouting operation would probably emphasize concealment and subtlety rather than outreach, demanding fresh approaches to identification. The consequences for SETI practices run deep. If cosmic travelers such as 3i Atlas indicate a real occurrence, then upcoming hunts need to extend past radio and light signals to involve routine scans for odd items inside our solar system. This change calls for innovative viewing tools, evaluation methods, and conceptual models to separate natural events from engineered ones. The most urgent effect involves upgrading systems for spotting and following interstellar objects. Existing sky scans, such as the Catalina Sky Survey and Linear, were built chiefly to spot risky asteroids, not cosmic intruders. Although these setups did pick up both Oumuamua and 3i Atlas, they fall short in precision and scope for thorough oversight of interstellar movement. Dr. Robert Warwick from the University of Hawaii's Institute for Astronomy, who headed the group that found Oumuamua, pushes for focused programs to survey interstellar objects. Such tailored setups would use broad-view telescopes equipped with cutting-edge image analysis software tailored to detect items on hyperbolic paths with atypical features. The aim is to catch interstellar arrivals early, out in the solar system's fringes, enabling prolonged study sessions and possible probe rendezvous efforts. The Vera C. Rubin Observatory, set to launch in 2024, marks a key advance in full-sky vigilance. Its massive survey telescope will image the whole observable sky every few nights, generating a vast archive of celestial data. This methodical strategy ought to greatly boost our capacity to spot and analyze interstellar objects, possibly showing if cases like 3i Atlas are isolated oddities or signs of ongoing cosmic journeys. Still, better spotting tools bring up tricky issues around analyzing data and upholding scientific rigor. The SETI field has wrestled for years with striking a balance between bold exploration and prudent conjecture. Assertions of possible alien encounters hold massive weight for humankind and demand compelling proof to back bold claims. The 3i Atlas example highlights this dilemma spot on. Although number crunching points to unlikely path traits, the proof stays indirect and open to other interpretations. Sharing tentative views could erode SETI's standing as a serious science, whereas too much restraint might lead experts to miss solid signs of alien presence. Dr. Seth Shostak from the SETI Institute calls for open disclosure of strange sightings while upholding strict analytical protocols are essential. The scientific process relies on transparent debates about data and its meanings. He states, "We must deliver facts impartially, making a sharp separation between factual findings and guesses regarding their meanings. This method calls for fresh guidelines in probing objects that could be man-made. Experts in SETI have crafted detailed rules for confirming and disclosing radio waves, demanding separate validations and expert scrutiny prior to any public reveal. Comparable benchmarks need to be set for tangible items that could indicate alien tech. The International Astronomical Union is now crafting systems for categorizing interstellar bodies and outlining study methods. Such guidelines stress methodical monitoring, data crunching, and joint efforts that curb personal prejudices or hopeful delusions. The aim is to define clear benchmarks for telling apart ordinary events from truly odd items that could justify bold assertions despite hurdles in spotting and examining them. 3i Atlas sparks deep inquiries into humanity's readiness for possible encounters with alien minds. Should scouting devices truly be exploring our solar system, they signal a type of interaction vastly unlike the far-off broadcasts SETI has expected for years. The mental and social effects of close extraterrestrial watching might be much tougher to handle than picking up transmissions from remote worlds. Distant signals, spanning thousands of light years, carry no urgent danger and give people space to absorb the meaning of such outreach. But solid presences in our own system imply direct curiosity about our society, prompting urgent puzzles over extraterrestrial motives and powers. Dr. Douglas Vakoch, head of Media International, stresses the urgency of pondering interaction cases with approaching vessels. For years, we've geared up for the chance of catching radio dispatches from far-off suns. As he points out, we're much less equipped for the idea that sophisticated societies could be observing us up close via scouting operations. This shortfall in readiness also affects official and organizational reactions. Although rules are in place for managing prospective SETI finds, they presume outreach via waves rather than actual arrivals. The 3i Atlas event underscores the demand for broad strategies covering every form of alien presence, encompassing situations needing swift action over thoughtful deliberation. The effects on policies for cosmic ventures are just as crucial. Should cosmic travelers actually roam our solar system, upcoming missions could run into crafted items or signs of alien doings. Cosmic bodies like agencies ought to factor in these risks in planning trips and crafting backup plans for surprise finds. NASA's Office for Coordinating Planetary Safeguards, set up to follow risky space rocks, is now weaving an oversight of interstellar wanderers to its duties. This broadening shows increasing awareness that quirky arrivals such as 3i Atlas deserve vigilant pursuit, no matter their true source. The branch's balanced attention to earthly dangers and possible crafted entities marks a key shift in how we watch the skies. Verifying a made-by-design source for something like 3i Atlas would mark humanity's greatest breakthrough ever, reshaping our view of where we fit in the cosmos. Such a verification would demonstrate advanced societies may exist out there, equipped with the means to journey between stars and intrigued enough by our solar system to explore it. Such a revelation would ripple far wider than just the field of astronomy, touching on philosophy, faith, governance, and virtually every facet of human society. That said, the bar for verifying this must stay exceptionally elevated. Scientific history is littered with cases where intriguing oddities turned out to have mundane rationales. Think of the Martian canals, the discovery of pulsars, once jokingly called little green men, or assorted supposed signs of life, all of which underscore the pitfalls of jumping to hasty judgments about alien presences. The 3i Atlas incident could well turn out to be yet another instance of our innate tendency to spot deliberate patterns in mere chance. Though its path defies statistical norms, it might just be an astonishing fluke instead of proof of intent. Only ongoing scrutiny and examination will settle these debates for good. Still, even should 3i Atlas emerge as wholly ordinary, its influence on SETI practices and perspectives will endure as significant. This interloper has shown that cosmic travelers can be spotted using today's tools, and that faint indicators of artificial makeup can emerge via meticulous data crunching. These insights will shape upcoming hunts, no matter what 3i Atlas truly is. The episode has further emphasized the need for cross-disciplinary teamwork in SETI efforts. Probing anomalies like 3i Atlas demands knowledge in areas such as celestial dynamics, probability modeling, substance properties, and many disciplines outside classic radio detection. Such joint ventures could be crucial for spotting and decoding truly engineered signals when they appear. 3i Atlas stands as either our species' greatest breakthrough or its grandest stellar happenstance. This 7-meter interloper from beyond our stars displays every trait the dark forest hypothesis anticipates. A precisely plotted course with odds of 1 in 2,000, an unspoiled makeup hinting at deep antiquity, and a lineup of close planetary passes that mimics a scouting operations script. Despite these peculiarities, the absent cometary vapors, the path's unlikely precision, the cleverly timed closest solar approach, 3I Atlas falls just shy of delivering the irrefutable evidence that we're sharing the cosmos. As it wraps up its sweeping pass through our system and vanishes into the void, this puzzling entity poses humanity's most compelling enigma. Are we observing initial outreach from the dark forest's quiet observers, or merely the cosmos's most striking quirk?